In this video, you will receive a general overview of electron configuration rules and how electrons can be distributed in an orbital diagram. Electrons occupy 3D regions of space called atomic orbitals. These orbitals vary in size and shape, and each can hold a maximum number of total electrons. Electrons tend to arrange themselves within the orbitals to give the atom the lowest energy as possible. When writing out the distribution of electrons, there are two main ways to show it. In this video, we will be showing orbital diagrams and convert them into electron configurations. Take note of the orbital diagram shown to your right for magnesium. We can gain a lot of valuable information from how the orbital diagram is set up. First, pay attention to the numbers that you see on the orbital diagram. Those numbers represent the principal energy level. The principal energy level represents the energy level or the position relative to how close to the nucleus it is. The principal energy level with higher numbers are found further away from the nucleus. The letters that you see represent the sublevel, and each sublevel has a different shape and total number of electrons that can be found in there. This can also be known as your subshell. There are 4 different types of orbitals that can exist, and each one has its own distinct shape and size. Your s orbital tends to be very spherical in shape. The p orbital looks like 2 balloons tied together. Your d orbital looks like 4 balloons tied together. And your f orbital looks like 8 balloons tied together. There are 3 main rules that define how the electrons are going to arrange within the atom. We will be covering all 3 of these. These include the Aufbau principle, Pauli exclusion principle, and Hund's rule. The Aufbau principle tells us that electrons will fill atomic orbitals of the lowest available energy levels before occupying higher energy levels. Take note of the orbital filling diagram found to our right. This shows all the different orbitals that exist and how they compare to one another in respect to energy. So what the Aufbau principle tells us is that we're going to be filling from lowest energy to highest energy as we are distributing our electrons. For example, we would first distribute electrons into our 1s orbital, then proceed on to our next highest one, which would be our 2s, followed by our 2p. And this pattern would repeat itself all the way through to the highest energy level. Again, I want to point out that the number that is shown with each of the orbitals represents the principal energy level, and the letter represents the sublevel or subshell that the electrons will be distributed into. Pauli exclusion principle states that no more than 2 electrons can occupy the same orbital, and that 2 electrons in the same orbital must have opposite spins. So let's take our 1s orbital for example. If we had a 1s orbital, what that means is if we were distributing our electrons, well, first, we could not have 3 electrons in there in any manner, whether that be the final one spinning up or spinning down. And we also could not have electrons that are facing in the same direction. What Pauli exclusion principle states is that within that orbital, you must have your electrons, only 2 of them, and they will be going in opposite directions. The final rule or principle that we're going to talk about is Hund's rule. Hund's rule states that every orbital in a subshell is singly occupied with 1 electron before 1 orbital is doubly occupied. So basically, we have to give 1 electron to each orbital within a subshell before we can come back and make a pair. So let's take our 2p orbital, for example. If we have a 2p subshell and we wanted to put electrons into the orbitals there, we know that there are 3 different types of p orbitals that exist in that subshell. And if we want to distribute up to 6 electrons into that subshell, we would first have to give 1 electron to each of the orbitals first in the subshell before we come back and make a pair. Again, what that means is if we were taking and distributing only, let's say, 4 electrons, we would not want to give 4 to those first 2 electrons like so. We would have to first give each we would have to first give each orbital 1 electron before we come back to make a pair. So now let's practice translating an electron configuration from an orbital diagram. Again, you can see the magnesium orbital diagram that we started with at the beginning of this video found to our left. Now all we're going to be doing is simply taking what we see in our orbital diagram and translating that into an electron configuration. So we would start at our lowest energy level, which is our 1s, and continue all the way up through the top. So, starting at the beginning, we would first say that we have a 1s orbital, and in that orbital we have 2 electrons. Now those 2 electrons that we see depicted as arrows are now going to be represented as superscripts next to that letter. So we would put the number 2 there. We would then follow it up with the next energy level, which is our 2s. And again, take those electrons that you see in the orbitals and represent them as a superscript with the number 2. We then move to the next highest energy orbital, which would be our 2p. And now we see that we have 6 electrons that have been distributed through, and we will write that as the number 6 up top. And then last but not least, we would take our 3s orbital, and we would depict those 2 electrons that are there as a 2 in the superscript position. Now notice, although in the orbital diagram you see empty 3p and 3d orbitals that are there, we are not showing them in our electron configuration because there are no electrons associated with magnesium that would be in those particular orbitals. So for the purpose of our electron configuration demonstration, this would be our final answer. So let's give this calcium example a try for practice. Starting with our lowest energy level, we would start at 1s, 2. Again, that 2 up top representing those electrons. Then we would go to 2s, 2. Then we move to 2p, 6. Then 3s, 2, followed by 3p6, and then last but not least, we would say 4s with the number 1 up top. Be sure to tune in to future videos to learn more about electron configuration and orbital diagrams.